All right, can you guys hear me online okay? Okay, great. All right, good morning.
Good morning.
Any
questions
about any of the
any of the material we've gone over so far?
Any general questions?
questions?
Yes.
Yes. They should be the same groups.
So
I'll
check that while we're working on another problem. Okay. Other yes.
So
as far
as
the
schedule goes, so today,
I'm getting feedback.
Okay.
So all right. I'm just hearing this feedback
going on in there.
Yeah,
there is an echo.
There we go.
Okay, I figured it out. I thought that one was muted. Okay. Hopefully there's not an echo anymore. All right, so timing next Monday will be the exam 2 group assignment that you did last time to prepare for the last exam, so you'll do the same thing. You will need to do a problem on, sorry, the partial fraction expansion, and then a couple problems in the S domain. So there'll be 3 problems that you'll need to do with your group. And so if you even want to start them again, it should be your same groups. I'll just check and make sure that they are connected the same way. So yeah, you can move around groups too still. If you want to move groups, you should be able to move around in groups. So if you've been working with people in here and want to stay with those same groups, that's fine. All right, any other questions, general comments? Yes.
So when you're saying complex, do you mean like complex numbers or just like?
I was trying to catch myself. Complicated input is what those should be, not that they are in the complex domain. And I apologize. I tried to catch that on most of those, but it will be complicated input, meaning just that it's an AC versus a DC source. Yeah, not that you'll, I mean, you could have a complex input. I mean, E raised to the minus, 4JT. You could have a complex input. You would treat it the same way. And we have not done anything like that. So I would not expect you to see that since we haven't worked on those. But it would be the same idea of solving the circuit. All right, any other questions, comments? Okay, question online was if I had posted the handouts. I did not get to post any handouts today, so you'll just have to unfortunately just take notes. And I grab the problem. Okay, so those should now be posted. All right, for those of you who have your laptops and want to download those notes, they're now on there. So if you want to work from them, so if this circuit shown here in circuit A is excited by a current waveform given by 9t e to the minus 3t u of t, and make sure you note that it's in milliamps, because that will make a big difference. So milliamps, determine I of t given R1 is 1, R2 is 3, and C is 1/3. Yes.
Say we were not given that unity on the IFS, when you still convert it into one form. Like, there's nine.
So if you were not given yeah, so if you didn't have a U of t function with it, you would still look for, you know, the, what do you call it? The transform, there we go. And so you would have to look at the transforms. Our tables all have U of t in them, so you'd have to look at different transform tables for them. So there is more transform tables for those. So note in this that you have in the time domain a t times the f of t. So this is a little bit different in that we're going to use the t f of t function. And then you have the t u of t. So what would you use? Oh, it's in the other. So if you don't have to use the differentiation, so note that you could do it either way. You could use the transform with the t times u of t, or you could try and do the time domain. Suggest that you try and do the one without the derivative in there. So take a minute to try to start solving that. Where did it go? Sorry, there you go. All right, so for you guys online, I'm just sharing it right now. So this will be the problem. And if you want to download it, it's on lecture 12 notes.
Oh, that's good. Yes. It's not. Yeah, this one is EX is equal to 9. Over S plus 3 squared divided by third times S plus 3 squared times R2 R1 plus S R1 R2 dx. I do this. Yeah.
I just. So it gets about, and then you end up like completely
I'm gonna do it here. Oh, I just made it. Yeah, I got Now all I'm gonna do is. Yeah. Yes, you can. So I can do that. We should. Yeah, we had that. It's in the textbook. Yeah. Yeah.
The reason I just like this is then I can take
That's wrong.
it's also
This is wrong. Because I'm scared. That form. Because it's you're doing 27. Oh, yeah, so it should be. I got minus. This is wrong. Minus 3 plus minus 2.
Oh, it's gonna be minus 4.
Right. No, you got 6. Okay.
Hi.
That's the answer to the previous one. So you got it. Thank you.
I told you.
Wait, isn't it? Okay, well, let's just what happens is this occurs right after 0. Why are you letting signs? I'm gonna solve. How about solve this? No. It's gonna be like again, if you get one
Yeah.
very small. Resistance. What is negative? All here. Oh, your current writer is so I know, right? You did that yesterday. Yeah, that's right. That was just. I kind of. You're supposed to take it, but I don't know how. It is.
All right. Okay. All right, to be able to solve this problem, first you need to transform into the S domain and then do KVL, KCL, node voltage, any other way of solving to get the equation set. And then from there, you're going to manipulate the solution to match the form of a Laplace transform on the table, and then do an inverse Laplace to change back to the time domain. So first step is transforming into the S domain. So when you do the transformation, you also need to look for the initial conditions. So the initial condition is going to be at right before an event happens or at time 0. And so in this case, your current is going to be 0. So with this equal to 0, that becomes an open. Your capacitor becomes a open also because it's been sitting there for a long time. And so this will be 0 for your initial condition. All right, questions on that? So when you do the 0, then your source that you would put either in series or in parallel, if it's in parallel, it's an open. And if it's in series, it becomes that wire. And so with that, this would be your circuit 1 over SC. R1 was 1. This becomes 3 over S. And this was 3. So changing those elements to the time or to this S domain, and then you have I of S, and using the table, I use this form, and then that gives you 9 times 10 to the minus 3. Why 9 times 10 to the minus 3 again? It's in milliamps, so make sure to account for that. It makes a big difference in your answer. So milliamps, so that's where the 10 to the minus 3 comes in. And then A in this case was 3. And then remember, when you have a number, it's just the same thing. You multiply it in the S domain also. So the 9 is on top. So this should be the transform of the input source. And then you can do either node voltage or a current divider. If you do a current divider, you need to combine the other two resistors, so you would have to combine these two resistors or two impedances. If you do a node voltage, you would have minus IS. I'll call that VX plus VX over 1, VX over 3 over S, and VX over 3. And then solve that for VX, and then I is gonna just be VX over 3. Did you see something?
Oh, yeah, sorry, no.
Okay. And then you should end up with this form. From here, you see you have a repeated root. So then you have A over S plus 4, B over S plus 3, and then B2 over S plus 3 squared. And you can either do, for this one, you can either do the derivative, or you can take the equation and multiply it by S plus 3 squared, which leaves you with S plus 4 on the bottom. And then you can plug in what you found for A and the B. And then each of these is multiplied by the S plus 3 squared. And then you can solve this to give you the B. Evaluate this at S equals so you could evaluate this at like S equals 0, which makes it a little easier. And then you should find the same value. Sorry, this was B. Sorry, this was B1. And then from here, you can change back into the man, I can't talk today. Let's see, we have a squared. Oh, I already have that one on there. Come on. So using this for the 1 over S plus 4 and the 1 over S plus 3, you get A is minus 4, or A is 4 in the first one, A is 3 in the second one. And then for the last one, you use again the squared version. And in this case, then A is still 3, and you just have T e to the minus 3t. All right, questions? Yes.
Would you look at it for your multiplier, and multiply by R1, but then like, why is it like R1 plus R2? It's that divider, that one.
So it needs to be R1 in parallel with, 3/S.
Yeah.
Is that what you're wondering? Okay. Becomes S3.
So how we did ours was we set these in parallel and then did a sort of transformation just to find that. But that would give us a new current then? That would be like the current from here plus the current from here. Is that?
Yes, so that would be those two currents, which doesn't.
So that's where we went. Yeah, because we had basically the same thing, except we just had a S numerator. So
Yeah, that was why. Okay, so his question was about how this ends up manipulating down into this form. So I'll work through the math to show you. And so you'll have that. Any other questions? Did everybody get this?
At what stage you apply this initial condition? I know the final condition, but then in what stage you apply the initial?
So the initial condition here is applied right at when you change into the S domain. So your initial condition is located here. So this is your initial. And I found that value to be 0. So I would put that into the value of the source here. Being 0, it's a wire. So it's done right as you change into the S domain.
So you use that initial condition to calculate REQ?
Yes, so you would, well, our REQ is only able to be done if you have them in parallel. If I had a source in there, I couldn't combine them into the same equivalent resistance. So I would have to use node voltage to solve that one. If I had a value other than 0 for my initial condition.
So here you solve the question by splitting into two parts. Initial condition, have an equation of REQ. And then the node KCL.
And then, yes, and then I solved the circuit.
Okay, yeah. I got it.
You got it? Okay. I can go through and do that while you guys are working on the next problem. Yeah, it is the same. Yeah. It is just that R equivalent times IS over R equivalent plus R2. All right, any other questions? Anyone feel like they got stuck somewhere? Want me to do some other algebra? I'm happy to try and see where you went.
R1 or 2 CS, R1 plus R2. I'm just confused about how you're R1 plus R2.
It's just manipulating this equation. I'll work on that while you guys work on the next problem to show you, so you don't have to wait for me to do all the math. So I'll show you where that came from. Any other questions? Yes.
Still just a little confused about the particle fraction expansion, just the
how it gets to.
Just A and B too?
Yeah.
Okay, so, this is just, multiplying this equation by S plus 4. So when you do that, you get A plus B1 over S plus 3 times S plus 4. I need more room. Oh, that. Okay, so it's just taking this times S plus 4. So when I multiply that by S plus 4, it cancels on the A. And then I get A plus B1 S plus 4 over S plus 3. B2 over S plus 3 squared. S plus 4. And then that is all equal to the 9 times 10 to the minus 3 S plus 4. So I'm taking this and this. And then these are going to cancel. And if I evaluate it at S equals minus 4, this goes to 0 and this goes to 0. So I'm just left with A is equal to 9 times 10 to the minus 3 over minus 4 plus 3 squared. Yeah, so you're multiplying that by the squared, which then does the same thing. It's going to cancel out on the bottom. And then it's going to remove the A and the B, the B1. And then for the B1, you can either take the derivative or you can use the ones you've already found and then just plug in an S that you haven't used before. So like S equals 0, and it will end up being the same. So either way can get you to the next one. All right, any other questions, comments? Didn't know where you went wrong? Happy to help. All right. Okay, any other questions online? It looked like you guys answered each other's questions, which is great. Any other questions? Okay, I posted another problem on the lecture 12. So if you want to download the next problem, sorry, I did not get to this last night. You can go ahead and download the next problem on here. This one is to give you practice also on having an initial condition. So in the past, we've always had that initial value of U of t has typically been 0. This time it's going to be 6. So you're going to have that current source has an initial value of 6 amps. So you're going to have to find that initial value in the capacitor and the inductor. So for this one, that extra step is to put the inductor as a wire, the capacitor as an open, and then a 6 value for IS. And that will give you your initial values for the capacitor and the inductor. Does that make sense? Okay, I'll repeat it again. So your time change here is at 0. And so right before that, I of S is going to equal this 6 amps. And so you use 6 amps as your initial value, and then you're redrawing the circuit with the capacitor and the inductor sitting for a long time. So in that case, you're going to have 6 amps is going to be your value here. And then you're going to replace the capacitor and the inductor to find the VC. And then this will be a wire to give you IL of 0 minus. What? That one will be 0. Right, because it's disconnected because of the capacitor.
That would be 6. That would be my VC.
So VC 0 minus will be 6 times R1. Yep. And then you need to redraw the circuit with those initial values in there. All right, for you guys online, I think I made an error last time when I was trying to put you into the breakout rooms, so I will try that again. If you guys want to screenshot this, or if you want to download it from the handout, lecture 12, I just updated it to have this in there also. Okay, I just opened all the rooms. If you guys want to move to them. Yes. It was just the way they did that. It's because you have, I don't know. I won't say, I didn't create the problem, so I don't know why you did that. Sorry, just 1 second.
For the
Yeah.
I used fiber provider, and I was want to make sure that I'm following the rules.
Okay.
So what I did was, I think I messed up with the math because my partial potential, I mean my setup is not correct.
Okay.
I'm not sure if I'm wrong, but
So where did you set up?
yeah. So right here, I combined the resistance of this and this, so that's 1 + 1 is 1 over 1 is 1 over
So when you combine them, I think that might be where it should be 1 over R1 plus 1 over.
it should be 1 over
Yeah, I mean, I guess it
R2S.
is, but it's,
I think this shouldn't just be, instead of 1 over 3 times S, it should be 1 over 3S.
yeah, this will be 1/3, so then it's 3 over S. I'm gonna do the math for this one, and then you can compare it to see if it's the same or not. If it is, then this would be, it would be the opposite branch, which would be those two combined all over that plus 3. So this setup is correct. Sorry. So let me do this one
Okay, yeah.
and then we'll see. Then you can compare it, because I know several other people that, they were wondering the same thing. So I'll move that down. I'll do that one really quick.
Sorry, I'm getting confused on your source transformation here.
Uh-huh.
Like where you have this, right? You're gonna have this constant 6 amps, and then
Yeah.
it goes to the function of 6 e to the negative 2t.
Uh-huh.
And my question is like, would you represent that, or is that wrong?
So
Is
it would
zero?
be kind of separated. So this would be before times 0, and this would be after times 0.
So it'd be like a
So
piecewise
there-
function.
Yeah, so you wouldn't have both, and then you're just using this for the initial conditions only. And so this is what's going to be used in the equation.
Okay, how do we know when we want to have a piecewise function? 'Cause I'm kind of confused.
Well,
there
you can't, I
because-
mean, this is not an accurate way of representing it. So the only way you can represent that is
Two parts.
2 parts, yeah.
But how do you like? How do you know that you're gonna have to? That's-
Just with how you can describe it mathematically. Like, if you were to graph this, you'll see it's not the same.
Oh, so this is kind of like the UFT function where you have one part where it's 0 and you just assume it's 0, and then another part where it's just immediately switched on to those things. So.
Yeah.
Okay.
Yeah,
Thank you.
so because you, I mean, if you did graph that, you would see it's not the same. And so you have to just match, mathematically what it will match up to.
Okay. And this is kind of like a decay function. And so this would be. All right.
Yep, so you just use that to solve the circuit as your source value.
All right. Thank you.
Uh-huh. S for 3 and then it goes down to 3 over S.
Oh, I see.
If you see then after that, what this rest of it is.
So remember this equation.
And that's kind of why that 60 was at. So basically, transform such and so that's going to have 60, you would have minus 60 meters. If you've already would be. Sorry, I was reading. I wrote it there. So versus 60, what if it's 60 really? Yeah, that makes sense.
And most of it. I suppose.
I know, I told
I'm doing some.
I'm getting there. I've got to the point where I'm submitting nice.
Yeah.
So you see it's this plus side, which is gonna be the top of here, minus side is gonna be the minus. So there is gonna be. Yeah, so it's gonna be across. Perfect.
Equivalent.
So the initial.
That's too right.
Pointing at each other. Oh, okay.
So source transformation, you basically using Ohm's law on the source that changes.
Yeah. Yes. You can find me She's right. Oh, you're so good. Yeah. Exactly what I love to say.
I just have a quick question unrelated to the problem.
Okay.
So for my next semester, is 37?
Just 1 second. So I think we've run out of time, so we're gonna pick this up on Monday. Yeah, if you want to. I'll, and I ran into an issue when I was doing the R equivalent, so I'll also work through that and post that in a little bit. All right, any questions before we go?
Yes. Right here, the ECE, is that as of the conflicts to me? Is that?
Sorry. Where'd it go? So, oh yeah, I see what you're saying. No, it's seconds, so it's 1/15 seconds. Sorry. Yeah, that will be seconds.
Yeah, that'll make it a lot less complicated.
Yeah, yep,
So then you just let this no value divided by that and get to the C. All right.
yep. Sorry, let me put this online. I realized I left them in the room. All right, welcome back. So we've run out of time for today, so I'm going to finish this up on Monday. And then I'm also going to supply some notes for the math so that you guys can look at it before Monday if you want to. Otherwise, I'll see you guys on Monday. Any problems or questions online? All right, see you guys.